Have you ever felt like your lab results are, well, part of some big mystery? Like you follow the procedure perfectly, but your answer is just off. Well, today, we're putting on our detective hats. We're going to investigate the scene, identify the culprits, and crack the case of analytical errors. So, let's dive right in.
So, here's the big question, right? The one that drives every analyst crazy. Why can't we just get the right answer every single time? I mean, if you've ever set foot in a chem lab, you know this feeling. But here's the good news. It doesn't mean you're a bad chemist, not at all. It just means we need to get a handle on the nature of measurement itself.
Okay, so think of it like this. Every single measurement we make is basically an attempt to find the true value of something. But what we actually get is our experimental value. And that gap, right, that unavoidable space between the truth and our result, well, that's what we call error. Now, our goal isn't to be some kind of superhero and eliminate all error, because honestly, that's impossible. The real job of a good analyst is to keep those errors small, tolerable, and to know exactly how big they are. So to really get a grip on this error, we've got to measure it. And for that, we have two main tools in our kit. First up is absolute error. It's super straightforward, just the simple difference between the true value and what you measured. But the second tool, relative error, now that's where things get interesting, because it's all about context. Think about it. An absolute error of, say, 0.02 is practically nothing if you're measuring something around 31, but that same 0.02 is a massive 50% error if your true value is only 0.04. See? The key takeaway is that context is everything. Relative error tells you the real story.
All right, so now that we know what we're looking for, it's time to meet our main suspects. You see, in any analytical investigation, the errors we find almost always fall into one of three distinct categories. Let's bring them in for questioning.
So here's our lineup. First, you've got your gross errors. Think of these as the clumsy, obvious blunders. Then we have systematic errors. These are the sneaky, consistent offenders that are always pushing your results in the same direction. And finally, they're the random errors, kind of like the unpredictable ghost in the machine that you can never quite pin down.
Let's kick things off with the easiest one to spot, gross error. This is that facepalm moment, you know? The kind of mistake that's so big and obvious, you know it the second it happens. You spill your sample, you grab the wrong chemical, you use a totally wrong piece of equipment. For you in the lab, the rule is simple. When this happens, you just stop. Document it in your lab book and start over. Seriously, don't even try to save that data. Case closed on that run.
Okay, now for a much more cunning suspect, systematic error. This one is tricky because it's so consistent. It'll make every single one of your measurements too high or every single one too low. It never goes back and forth. So this error, it's a direct attack on the accuracy of your result, how close you are to that true value. But here's the crucial part, the good news. Because it's so consistent, we can actually find it and correct for it. This is the one error you can actually outsmart.
And our final suspect is random error. Honestly, this one isn't really a suspect we can catch. It's more like a fundamental property of the universe, just part of the deal. Think of it as the sum of a million tiny, uncontrollable variables, a little draft of air, a tiny temperature change, a vibration from the floor. It causes your results to scatter randomly around a central value, and it directly affects your precision. That's how close your repeated results are to each other. So here's the big difference. Unlike systematic error, you can't fix this one. You can only learn to manage it.
Okay, so let's zoom in a bit. It's time for a deep dive, and we're going to focus our investigation squarely on systematic errors. Now, you might be asking, why this one? Well, it's simple, because unlike the other two, this is the one we can truly investigate, identify, and ultimately outsmart.
So when we put a systematic error under the interrogation lamp, we find it usually comes from one of three places. First, it could be a methodic error, which means the chemistry of your procedure itself is flawed. Second, it might be a personal error, something that comes from the analyst's own bias or technique. Or third, it could be an instrumental error, where the gear you're using just isn't telling you the whole truth. And this right here is a perfect example of a classic methodic error in action. So, imagine you're doing a titration. The true equivalence point, that sweet spot where the reaction is perfectly complete, is at a pH of 7. But what if you choose an indicator like phenolphthalein? That definitely changes color way up around pH 9. What happens? Well, you will consistently, every single time, add too much titrant. The method itself is forcing you to get a systematically high result. Now, what's interesting is that these systematic errors don't all behave the same way. They tend to follow one of two distinct patterns.
You've got your constant error, which has a fixed size. For example, maybe you lose exactly 0.5 milligrams every time you weigh something, no matter how big the sample is. Then, on the other hand, you have proportional error. This one actually gets bigger as your sample gets bigger. Think of a contaminant that always makes up, say, 1% of your sample's total weight. So let's really see how this plays out, okay? Look at the example on the left. With a constant error, that same 0.5 milligram loss has a huge relative impact on a small sample, but a really tiny one on a large sample. The absolute error stays the same, but how much it matters changes. Now shift your eyes to the right. With a proportional error, notice something? The relative error stays at a constant 10% no matter how big the sample is. The error just scales right along with it.
So the big question is, how do we catch these errors? Well, this is your detective toolkit. For personal errors, it's all about care, focus, and just playing good technique. For instrumental errors, you hunt them down and correct them by calibrating your equipment against known standards. And for the trickiest ones, the methodologic errors, you need some clever techniques, like analyzing standard samples or running what's called a blank determination. Let's put one of those tools under the spotlight, the blank determination. This is such a brilliant move. Here's how it works. First, you measure your real sample and you get a result, in this case, an absorbance of 0.85. Okay, then you run the exact same procedure, but this time you replace your sample with just distilled water. You're blank. Any reading you get now, like this 0.02 you see here, well, that has to be coming from your reagents or the instrument itself. And just like that, you've isolated the error. Now you can just subtract it from your real measurement to get a much more accurate, corrected result. So cool.
Okay, we've really put systematic errors under the microscope. But what about that last member of our lineup? It's time to turn our attention to that elusive random error, the ghost in the machine.
Now, it's super important to remember, random error isn't a mistake. It's not something you did wrong. It's the combined effect of countless, tiny, unpredictable variables that are always there. We can't point to one single cause, and we absolutely can't get rid of it. What this means is that random error sets the ultimate limit on the precision of your experiment, and our only real weapon against it? It's statistics.
And this is where things get really, really cool. This shows how something that's totally random can actually become predictable. Look at that top graph. With just 4 measurements, the data's all over the place, right? It just looks like a mess. But watch what happens as you collect more and more data. 20 points, 50, 200. All of a sudden, a shape starts to emerge. And by the time you get to 1,000 measurements, that seemingly random scatter has organized itself into this beautiful, symmetrical, bell-shaped curve. This incredible pattern is called the Gaussian distribution, or sometimes the normal distribution, and it is the absolute key to understanding random error. It tells us 3 really important things. First, the most frequent result you're going to get is the average value, right there in the middle. Second, small errors away from the average are pretty common, but huge errors way out on the sides are super rare. And third, you're just as likely to have a small error that's a little too high as you are to have one that's a little too low. So even though we can't predict the next single error, we can predict the overall pattern of thousands of them. That's powerful. So, after all that investigation, we've identified our culprits, and we've figured out their methods. I'd say it's time to write up our final report. Think of this as your ultimate summary, everything you need for understanding and acing the evaluation of analytical data.
Let's break it all down one last time, nice and simple. Gross errors. Those are the big, obvious mistakes. They invalidate your result, and the only solution is to start over. Systematic errors. These are the consistent biases that mess with your accuracy. You fix them by calibrating and refining your method. And finally, random errors. Those are the unavoidable, unbiased fluctuations that affect your precision. You can't fix them, but you manage them with more measurements and good old statistics. And that's pretty much the whole case, right there.
So there you have it. We've cracked the code. You now have the forensic toolkit you need to analyze not just your data, but your entire experimental process. The next time you step into the lab, you're not just the student, you're a detective. You know exactly what to look for, and you know how to build a much stronger case for your results. So the only question left is, what will you discover?